Future Energy, Thorium and the LFTR reactor by Steve Hay, August 2013. Text and graphics for this presentation is available at 2112design.com/blog/LFTR. Thorium is a relatively abundant metal found in the Earth's crust. It is forged in the cores of dying stars and scattered across the galaxy by supernovas. It arrived here 4.5 billion years ago in the formation of the Earth. Thorium decay produces a significant amount of the Earth's internal heat. Thorium is about as common as lead, 4 times more common than uranium, and is produced and usually discarded as a byproduct of mining rare earth metals, used to make magnets for motors. Thorium is cheap and plentiful, but by itself, is not a nuclear fuel. Natural thorium decays very slowly compared to many other radioactive materials, and the alpha radiation emitted cannot penetrate human skin. Handling small amounts of thorium is considered safe. In today's light water reactors, it takes 250 tons of natural uranium to produce 1 gigawatt of electricity for 1 year. 1 gigawatt is about the average size of a typical, current generation, nuclear reactor. The USA currently has total electricity generating capacity of 1,050 gigawatts, of which about 20%, or 200 gigawatts, is from nuclear. A 1 gigawatt light water reactor produces 20 to 35 tons of spent nuclear fuel, which is highly radioactive for 10,000 to 1 million years. By comparison, a theoretical thorium-based LFTR-type reactor consumes 1 ton of cheap thorium and produces 1 ton of waste, most of which is radioactive for 10 years, the remaining for 300 years. To replace all coal, gas and conventional nuclear generating capacity in the U.S. with LFTR reactors, would theoretically require 929 tons of thorium and produce 929 tons of waste per year. So, to replace all current U.S. coal, gas and nuclear generation capacity, requires just 3 standard 40-foot shipping containers of thorium per year, and produces about the same amount of waste. Currently, the U.S. generates 2,000 tons of nuclear waste per year, to generate 838 terawatt-hours per year of electricity. To produce the same amount of electricity in a year, a thorium-based LFTR reactor would produce 8.7 tons of waste. Why are we still talking about fission? Isn't fission bad? Many people will turn off at the mention of the word fission. After all, look at Fukushima, Chernobyl, and 3 Mile Island. Why not use solar, wind, and the holy grail of future energy, fusion? I think we will, but thorium fission has in the medium term, the potential to greatly reduce our reliance on fossil fuels. Part 1, Thorium Fuel Cycle. Thorium is not a nuclear fuel, it is not a fissile material, meaning it cannot maintain a nuclear chain reaction, and therefore produce energy, by nuclear fission. Thorium must be used in conjunction with uranium, specifically, U-233, to produce energy in the thorium fuel cycle. The reaction starts when a neutron crashes into a uranium-233 atom. U-233 is an isotope of uranium. Isotopes are variants of an element. All isotopes of a given element share the same number of protons, they differ in the number of neutrons. The 233 in U-233 means there are a total of 233 protons and neutrons in the nucleus of the atom. Uranium-233 is not a naturally occurring element, it is not mined from the Earth, like U-235 used in conventional nuclear reactors. It is produced by bombarding thorium with neutrons. If a neutron hits a U-233 atom, it has a chance of getting captured by the nucleus, and if it does, the atom undergoes nuclear fission. Each atom splits into 2 new atoms, like xenon, silver, palladium, molybdenum, plus 2 or 3 free neutrons and a lot of energy. It's this energy in the form of heat, that we are ultimately interested in, to make electricity. The 2 new elements that are produced are called fission products. They are basically unwanted waste products. It's the 2 or 3 neutrons that we are interested in, because they can go on to hit more U-233 atoms and produce a self-sustaining chain reaction, producing more heat and more neutrons, as long as there is U-233 to fuel the reaction. So at this point we are already producing a lot of energy, simply by packing a lot of U-233 into a relatively small space, to create what is called criticality, meaning every fission causes an average of one or more fission reactions. The problem is, sooner or later the U-233 nuclear fuel will be used up, and it's expensive to make more. This is where thorium comes to the rescue. Thorium in nuclear scientist speak is a fertile element. Without getting into details, think of it as fertilizer. You can't eat it directly, but you need it to grow your food. That's exactly what thorium does in the thorium fuel cycle. It breeds more fuel, namely U-233. When thorium-232 gets hit by a neutron, it has a chance of capturing the neutron, which transmutes it into thorium-233. Thorium-233 then quickly decays to protactinium-233, which after about 30 days on average, decays into U-233. This U-233 can be separated from the thorium and protactinium and put back into the core, to provide a limitless supply of fuel. The thorium is consumed by this reaction, so needs constant replacement. However, there is one small glitch. The neutrons resulting from the fission of U-233 are traveling very fast. Like trying to catch a bullet from a gun, they are very hard for the thorium and uranium atoms to capture. By passing the neutrons through carbon-12 and graphite, the neutrons are slowed down like a speeding bullet going through honey. The neutrons coming out of the carbon-12 are traveling at close to the same speed as the thorium, so like in our honey bullet analogy, they are very easy to catch. In this state, the neutrons are called thermal neutrons, meaning they're in thermal equilibrium with their surroundings, the same temperature as the U-233 salt. If you remember your physics, you'll know temperature is measurement of a particle's velocity or kinetic energy. Heat is simply excited atoms. And so we have the thorium fuel cycle because it goes around in a never-ending loop, where U-233 atoms undergo fission to produce energy, neutrons and waste products. Then neutrons and thorium produce more U-233. Then by reusing the U-233, topping up the thorium and removing the waste products, the system can produce energy for as long as the reactor lasts. And even after that, the U-233 and thorium can be used in new reactors. Part 2. Liquid fluoride thorium reactor. There are several substantially different ways to design a nuclear reactor, to use the thorium fuel cycle, but the one that potentially has the most promise and interest at the moment is the liquid fluoride thorium reactor, or LFTR, lifter. In this example of a two-fluid lifter reactor, the cycle starts with a neutron floating in a soup of uranium-233 liquid fuel salt in the fissile core of the reactor. Fissile core means that's where all the fission takes place. The uranium fuel salt soup is composed of U-233, a metal at room temperature, dissolved into a molten salt solution. This is not the kind of salt you put on your chips. It's composed mostly of beryllium and lithium fluoride, at about 600 degrees C, at atmospheric pressure. Beryllium and lithium are relatively rare, expensive and highly toxic metals, but are not consumed by the reactor. Once the reactor is fueled, the beryllium and lithium rarely need topping up. The reactor core runs close to atmospheric pressure, which is a huge safety advantage over conventional reactors, which typically use high-pressure water to cool the core. Also, because the reactor runs at high temperature, it is far more efficient in producing electricity from heat than conventional nuclear reactors. When a neutron is captured by a U-233 atom, fission produces two new elements called fission products, 2 or 3 neutrons and lots of heat. In the lifter reactor, the U-233 molten coarse salt is pumped through a heat exchanger to extract the heat to boil water into steam, or heat gas for a gas turbine. and then onto an electrical generator and onto the power grid. Generating electricity from heat like this is conventional technology in all coal, gas and nuclear power stations today. The secondary coolant going to the turbine is at high pressure, but the coolant used is water or a harmless gas such as helium, nitrogen, or carbon dioxide, and this part of the system is not radioactive. In the event of an accidental release of the high-pressure secondary coolant, no radiation would be released. In a practical system there may be two or more sets of heat exchangers, to further isolate the high-pressure steam or gas in the turbine, from the highly radioactive low-pressure core. The fission products are basically unwanted waste products that need to be removed from the core, or they will poison the reaction, that is absorb neutrons, slow down the chain reaction and eventually kill it. A key feature of the lifter design is that fission products are separated from the U-233 salt solution continuously, without shutting down the reactor, a major advantage over traditional nuclear reactors which need to shut down every few years to reprocess the solid fuel. Lifter reactors need never shut down in their normal working life, so providing better overall economy of operation. Fission products are separated from the U-233 and salts by a relatively cheap and simple chemical process called pyroprocessing. There is no need to make the fuel salt very clean, the purpose is to keep the concentration of fission products and other impurities, like oxygen, low enough. It is not necessary to clean all the salts all the time. Nuclear fission in the core continues in a controlled chain reaction, moderated by control rods inserted into the core. Control rods are made of neutron-absorbing material, like silver or cadmium. Surrounding the U-233 fissile core, is a blanket of thorium-232, the fertile blanket. As you may recall from the thorium fuel cycle, this is where thorium is the fertilizer that breeds more U-233 fuel. Like the U-233, the thorium is dissolved in a hot salt of beryllium and lithium at the same temperature and pressure as the core. In a one-fluid lifter reactor, the U-233 and thorium are mixed together in a single core, which is mechanically much simpler than the two-fluid core and blanket design. One-fluid reactors are simpler to build, but have greater difficulty of separation of waste products and U-233 from the thorium. However, it is important to realize this example is not the only lifter reactor design currently being studied or proposed, and the working first lifter reactor likely to be built will probably be a single fluid design. Fast neutrons produced in the core, pass through the graphite core wall, and slow down to become thermal neutrons, so they are moving at the same speed as the thorium atoms. Because of this, most of the neutrons are captured by the thorium, resulting in high-efficiency breeding, and less leakage of high-energy neutrons into the reactor containment walls. Thorium-232, plus a neutron, transmutes to thorium-233 which decays to protactinium-233 which decays after a few weeks to uranium-233. A chemical separation system removes the U-233 from blanket salts, and returns them to the core to provide a continuous supply of fuel forever, so long as there is thorium fertilizer. The reactor can be designed to be break-even in the amount of U-233 it produces and consumes, up to about 9% more U-233 than it consumes, so the excess can be used to start new lifter reactors. Because thorium is used up in this process, it must be periodically replaced at the rate of about 1 ton per year for a 1 gigawatt reactor, which is 2.7 kilograms per day, something you could hold in the palm of your hand. And remember, it produces the same amount of waste, about 1 handful per day. As a safety feature of this design, there is an emergency drain pipe at the bottom of the core, to a dump tank, of neutron-absorbing materials like boron or cadmium. The dump tank is below the core, so gravity transports the core salts to the dump tank in case of an emergency. The drain pipe is normally blocked by a freeze plug. This plug is frozen core salts, frozen in this case meaning about 200 degrees C, which is below the melting point of the salts. The freeze plug is kept frozen by a fan. If there is a catastrophic failure of power to the reactor cooling system, such as in the Fukushima nuclear plant, and the shit hits the fan so to speak, the fan will stop working, the plug will quickly heat up, and the core salts will drain into the dump tank. The neutron absorbers will instantly kill the fission chain reaction, and in a few hours the core salts will solidify, with no release of radiation outside the dump tank. Additionally, there is an overflow pipe at the top of the core leading to the dump tank. If the core overheats, but the freeze plug fan still has power, the core salt liquids will expand through thermal expansion. This will cause core salts to flow out under their own pressure into the dump tank, reducing the amount of fissionable material in the core, and cause it to cool down. These are some of the major advantages of molten salt reactors, over solid fuel reactors, in use today. The emergency shutdown system does not require people, computers, pumps, electricity, etc. It is totally passive and automatic, relying solely on conduction heating, thermal expansion, and gravity. Part 3, Lifter Pros and Cons. The following is a summary of the Wikipedia LFTR page. Warning: this section is a bit boring. You may want to skip to the 28-minute mark if you are not interested in the following details. Lifter advantages. Thorium-fueled molten salt reactor offers many potential advantages compared to conventional solid uranium-fueled light water reactors. Inherent safety. If the core salts overheat, they expand considerably due to the liquid nature of the fuel, and will push fuel out of the active core region. Also, thorium absorbs more neutrons if it overheats, leaving fewer neutrons to continue the chain reaction, reducing power. Stable coolant. Molten fluorides in the core and blanket salts are chemically stable and impervious to radiation. The salts do not burn, explode, or decompose, even under high temperature and radiation. There is no combustible hydrogen production that water coolants have. Low pressure operation. Because the coolant salts remain liquid at high temperatures, lifter cores are designed to operate at low pressures or about 0.6 megapascals, the pressure of your house's water pipes. Lifter coolant salts have very high boiling points. Even a several hundred-degree heat up does not cause a meaningful pressure increase. There is no water or hydrogen in the reactor that can cause a large pressure rise or explosion as happened during the Fukushima Daiichi nuclear accident. Leak resistance. Due to the low pressure operation, the reactor plumbing is not under high stress from high pressures, so the potential for large leaks is greatly reduced. No pressure buildup from fission. Lifters prevent pressure buildup due to gaseous and volatile fission products. The liquid fuel allows for continuous removal of fission products, so they would not be spread in the event of a core breach. Easier to control. Xenon-135, an important neutron absorber, and makes solid-fueled reactors difficult to control. In a molten-fueled reactor like a lifter, Xenon-135 can be removed continuously. Fail-safe core. Lifters can include a freeze plug, at the bottom of the core, into a neutron-absorbing dump tank as discussed already. Less long-lived waste. Lifters can dramatically reduce the long-term radiotoxicity of their reactor wastes. Light water reactors have fuel that is more than 95% U-238. These reactors normally transmute part of the U-238 to plutonium with a half-life of 24,000 years. In contrast, lifters use the thorium fuel cycle, which transmutes thorium to U-233. U-233 has a 98% chance to fission to more U-233 or U-235 fuel. 2% of remaining fissions can produce radiotoxic waste at about 15 kilograms per gigawatt per year. These transuranic products, bad shit, are 20x smaller in lifters than light water reactors. Destruction of existing long-lived wastes. Lifters can use existing nuclear waste such as plutonium for their initial startup, so they can actually help reduce current stockpiles of nuclear waste. Proliferation resistance, nuke safety. The lifter's design makes it more difficult for diversion of its fuel to nuclear weapons in 4 ways. First, The thorium-232 breeds a small amounts of U-232 which emits powerful, dangerous gamma rays. These gamma rays are not a problem inside a reactor, but in a bomb, they complicate bomb manufacture, harm electronics and reveal the bomb's location. Secondly, lifters produce very little plutonium, around 15 kilograms per gigawatt-year of electricity. This plutonium is also mostly plutonium-238, which makes it unsuitable for fission bomb building, due to the high heat and spontaneous neutrons emitted. Thirdly, a lifter doesn't make much spare fuel. It produces at most 9% more fuel than it burns each year, and it's even easier to design a reactor that makes 1% more fuel. And finally, use of thorium can reduce or even eliminate the need to enrich uranium. Uranium enrichment is one of the two primary methods by which states have obtained bomb-making materials. Comparison of annual fuel requirements and waste products of a 1 gigawatt uranium-fueled light water reactor, and a 1 gigawatt thorium-fueled lifter power plant. Thorium abundance. A lifter breeds thorium into uranium-233 fuel. The Earth's crust contains about 4 times as much thorium as U-238. Thorium is about as abundant as lead. It is a byproduct of rare earth mining, normally discarded as waste. Using lifters, there is enough affordable thorium to satisfy the global energy needs for hundreds of thousands of years. No shortage of natural resources. Sufficient other natural resources such as beryllium, lithium, nickel and molybdenum are available to build thousands of lifter reactors. Reactor efficiency. Conventional reactors consume less than 1% of the mined uranium, leaving the rest as waste. A lifter can consume about 99% of its thorium fuel. The improved fuel efficiency means that 1 ton of natural thorium in a lifter produces as much energy as 35 tons of enriched uranium in conventional reactors, requiring 250 tons of natural uranium, or 4,166,000 tons of black coal in a coal power plant. Thermodynamic efficiency. A lifter reactor operating with modern supercritical steam turbines, would operate at 45% thermal to electrical efficiency. This is 20 to 40% higher than today's light water reactors. No enrichment and fuel element fabrication. Since 100% of natural thorium can be used as a fuel, and the fuel is in the form of a molten salt instead of solid fuel rods, expensive fuel enrichment and solid fuel rods validation procedures and fabricating processes are not needed. Lower startup costs. For a 1 gigawatt 2-fluid lifter, the startup costs could be something like this. 99,000 kilograms of thorium costs about $2.9 million. 700 kilograms of uranium-233 costs about $70 million. Assumes expensively produced from enriched plutonium. Could be a lot cheaper if using nuclear waste from existing reactors. 26,000 kilograms of beryllium as BIF2 costs about $3.8 million. 66,500 kilograms of lithium as LIF costs about $8 to $53 million. Total, $85 to $130 million. This is about half the cost of a first core for a light water reactor, and the salt inventory can last for decades, whereas the light water reactor needs a completely new core every 4 to 6 years. Lifters are cleaner, as a fully recycling system. The discharge wastes from a LFTR are predominantly fission products, most of which have relatively short half-lives. This results in a significant reduction in waste containment. No downtime for refueling. Lifters have liquid fuels, and therefore there is no need to shut down and take apart the reactor just to refuel it. Lifters can refuel without causing a power outage. Load following. As the lifter does not have xenon poisoning, there is no problem reducing the power in times of low demand for electricity and turn back on at any time. No high pressure vessel. Since the core is not pressurized, it does not need the most expensive item in a light water reactor, a high pressure reactor vessel for the core. Instead, there is a low pressure vessel, and pipes for the molten salt, constructed of relatively thin materials. Excellent heat transfer. Liquid fluoride salts, especially LIF-based salts, have good heat transfer properties. The lift-based salts have a thermal conductivity around twice that of the hot pressurized water. This results in efficient heat transfer and a compact heat exchanger. Air cooling. A high-temperature power cycle can be air-cooled at little loss in efficiency, which is critical for use in many regions where water is scarce. No need for large water cooling towers used in conventional steam-powered systems. Lifter challenges. Lifters are quite unlike today's operating commercial power reactors. These differences create design challenges and trade-offs. Startup fuel. Uranium-233 is not a naturally occurring element. It must be manufactured from thorium, so a reactor fueled by a fissionable product, like waste plutonium, must be built first to manufacture U-233 to start a lifter. Salts freezing. The fluoride salt mixtures have melting points from 300 to over 600 degrees C, depending on the mixture. The salts, especially those with beryllium fluoride, are very viscous close to their freezing point. This requires careful design and freeze protection in the containment and heat exchangers. Uncontrolled freezing must be prevented, or the reactor would be damaged, like ice in your car's radiator. Beryllium toxicity. The proposed salt mixture FLiB contains large amounts of beryllium, a poisonous element. The salt in the primary cooling loops must be isolated from workers in the environment to prevent beryllium poisoning. Waste management. There is also a need to manage the waste, which is still very radioactive, even though it is hazardous for a shorter period. Noble metal buildup. Some radioactive fission products, such as noble metals, don't form salts, but deposit on the pipes. Novel equipment, such as nickel wool sponge cartridges, must be developed to filter and trap the noble metals to prevent buildup over time. Limited graphite lifetime. Compact designs have a limited lifetime for the graphite moderator and fuel breeding loop separator. Under the influence of fast neutrons, the graphite first shrinks, then expands indefinitely until it becomes very weak and can crack. Proliferation risk from reprocessing. A lifter reactor produces far less radioactive waste than a conventional reactor, but it does produce some, which could fall into the wrong hands. See Wikipedia for more detailed explanation. Corrosion and radiation damage to reactor. More research is needed on the long-term effects of lifter's operation on the materials used for its construction. Long-term fuel salt storage issues. If the fluoride fuel salts are stored in solid form over many decades, radiation can cause the release of corrosive fluorine gas, and uranium hexafluoride. Business model. Today's solid-fueled reactor vendors make long-term revenues by fuel fabrication. Without any fuel to fabricate and sell, lifters would adopt a different business model. Part 4, The Big Energy Picture. Burning fossil fuels accounted for 67% of the world's electricity production in 2008. Most scientists agree that burning coal, gas and oil, producing CO2, is heating the planet, causing rising sea levels and extreme weather, and that existing nuclear power is expensive and produces huge waste problems. Hydroelectric power isn't much better, as it impacts millions of people, with loss of land, and in some cases produces more greenhouse gas emission than an equivalently sized coal plants. But what are the alternatives? Renewables, solar, wind, tidal and wave power are all starting to make contributions to the world energy supply, but are fundamentally limited by the problem that they don't produce power. When the sun doesn't shine, the wind doesn't blow, or it's slack tide. People will always want power 24 hours a day, 7 days a week, so there will always be a need for baseload power. Some existing and under construction solar thermal power plants do have the ability to produce power 24/7, by storing heat overnight, in a big tank of molten salt. But even they will run out of juice if the sun doesn't shine for a day or two. Also, solar, wind, tidal and wave power have to be located where the resource is most economically available, like hot deserts and shorelines. This requires that the power be transported long distances, at great loss and expense, to consumers, often hundreds or thousands of miles from the renewable power sources. Geothermal energy, extracting heat from deep underground by drilling a hole and pumping water in, to produce steam, can provide baseload power and currently supplies 0.3% of US and a massive 30% of Iceland's electricity production, but is not without problems. Wells may cool down over time, and there is the risk of groundwater contamination and small earthquakes. Of course, the pot of gold at the end of the energy rainbow is fusion, recreating the power of the sun here on Earth. Thanks to Albert Einstein and E=mc², it is theoretically possible to generate all the world's electricity needs, with a few tons of seawater. But to do that, you need to heat up hydrogen isotopes, deuterium and tritium, to 150 million degrees C, which is 10 times hotter than the core of the Sun, at astronomical pressures, and keep it there while you add more fuel. It is possible, and it's been done already on a very small scale, but never to the point where it produces more energy than it consumes, not by a long way. The world's biggest and best hope research project into nuclear fusion is the LFTR reactor in France, due to be operational in 2027, 14 years from now. However, LFTR is only a research reactor designed to produce approximately 500 megawatts of fusion power, sustained for up to 1,000 seconds. Plans for building full-scale power-generating fusion plants will depend on the result from LFTR and other experiments, but is highly unlikely to be available to contribute any meaningful power to the world in less than 30 years, and given the engineering challenges, it may be a lot longer. With thorium fuel cycle and the LFTR reactor, the physics is well understood and the materials and techniques required to build a working reactor are not that much different from existing 50-year-old nuclear technology. In fact, we've already proved the basic design of a molten salt reactor in 1964, with the molten salt reactor experiment at the Oak Ridge National Lab, in Tennessee. Part 5, Thorium, LFTR, Yesterday and Today. The thorium fuel cycle has been well understood for over 50 years. In 1964, the molten salt reactor experiment was a 7.4 megawatts test reactor simulating a type of LFTR reactor. It primarily used two fuels, first uranium-235 and later uranium-233. The U-233 was the result of breeding from thorium in other reactors. According to LFTR pioneer Kirk Sorensen in the YouTube video, The Thorium Molten Salt Reactor, Why Didn't This Happen?, the MSR program was defunded in 1976 after its patron, Alvin Weinberg, was fired for pointing out the inherent dangers of the fast breeder reactors while the US government and industry had already put all their efforts into fast breeder reactors.
After all, we were pushing molten salt, not the fast breeder. More than that, we were being troublesome over the question of reactor safety. And that was another aspect that was getting Weinberg into trouble. He had invented the pressurized light water reactor that formed the backbone of the reactor technologies that were being developed in the country at that time. Here's a picture of some of the pressurized water reactors. His work on the thorium reactor led him to believe that a significantly higher level of safety was possible. And this, in large part, was because the thorium reactor operated at low pressures, whereas water-cooled reactors operated at high pressures. So he was beginning to bring these issues up in support of the thorium reactor. But it didn't have that effect. Congressman Chet Holofield was clearly exasperated with me, and he finally blurted out, "Alvin, if you're so concerned about the safety of reactors, then I think it might be time for you to leave nuclear energy." But I was speechless. But it was apparent to me that my style, my attitude, and my perception of the future were no longer in tune with the powers within the AEC. And I think this was a very sad moment in the history of our country and probably in the history of the world, because an entire direction of potential development was being ended at that moment by a not well thought out comment by Congressman Holofield, who was very powerful. Weinberg looked at this fairly philosophically when he wrote his autobiography in 1994. He said, "I look back on these events, I realized that leaving Oak Ridge was the best thing that could have happened to me. My views about nuclear energy were at variance with those of the AEC and congressional leadership. After all, it was I who had called nuclear energy a Faustian bargain, who continued to promote the molten salt breeder. So Weinberg's pursuit of thorium appears to have had a great deal to do with why he was fired from his position at Oak Ridge in the Atomic Energy Commission. And it's not hard to see, when you stack up the forces that were in support of the fast breeder and that effort, the money, the industrial backing, the confidence they had, and here is Weinberg trying to push something different, why they would attempt to truncate his work. The upshot of that was, in January of 1973, Oak Ridge was directed by the Atomic Energy Commission to terminate the development of the molten salt reactor.
According to another YouTube video, The Thorium Conspiracy, Stuff They Don't Want You to Know, thorium research was closed down in the 60s, the Cold War, because thorium-based reactors don't produce plutonium, needed at the time for atomic bombs. Thorium power was killed because it was too safe.
According to the U.S. Department of Energy, early nuclear research before and during World War II focused on the development of weapons, and it was only later that scientists began focusing on peaceful applications of nuclear technology. Consider that the first atomic bomb was tested in 1945, but the first investigation of peaceful atomic energy did not begin until 1947. Since the original focus of the U.S. research was on military applications, uranium became the superior choice. As Forbes writer Marin Katusa points out, uranium's reaction process generates plutonium-239, which can be weaponized. Thorium, despite its potential advantages, does not. Experts at Oak Ridge National Laboratory in Oak Ridge, Tennessee had already built a thorium reactor by the 1960s, and it was shut down under the Nixon presidency not because it didn't work, but because it didn't produce plutonium.
In 1977, the Shippingport Atomic Power Station was fitted with an experimental core thermal breeder reactor, and is notable for its ability to transmute thorium-232 to uranium-233. In more recent times, it's probably the case that the big nuclear power plant manufacturers like GE, Hitachi, Toshiba etc. have a lot invested in current technology and don't want the expense and delay of trying something new. So it seems the biggest problem with thorium and lifter progress is politics, not science and technology. However, even though lifter reactors appear to have very significant advantage in operational cost and safety over existing nuclear technology, they are still not without risk. While it would be close to impossible to build a bomb from lifter byproducts, the U-233 in the lifter core is still an extremely dangerous radioactive material. A conventional bomb dropped on, or in, a lifter plant could spread radiotoxic material for many miles and contaminate the area for thousands of years, so lifter plants would need security like all existing nuclear plants. However, there is renewed interest in thorium and lifter reactors, especially in China, India, and Japan. The Chinese Thorium MSR project has a startup budget of $350 million. There is currently 140 PhD scientists, working full-time on thorium power at the Shanghai Institute of Nuclear and Applied Physics. The project will have 750 staff by 2015. The target completion date for its test 2 MW thorium molten salt reactor is 2020, followed by a 10 MW demonstrator reactor, and an 100 MW pilot. The Fuji molten salt reactor is being developed by the Japanese company Thums, together with partners from the Czech Republic. They have chosen a single salt design to save complexity. The proposed design is rated at 200 megawatts. The consortium plans to first build a much smaller mini Fuji 10 megawatts reactor of the same design, once it has secured an additional $300 million in funding. India's government is developing up to 62. Mostly thorium reactors, which it expects to be operational by 2025. These are not necessary lifter reactors but a combination of new and old technology which may or may not have the benefits of lifter reactors. In late 2012, Norway's Thor Energy announced that they will conduct a 4-year trial using thorium as a nuclear fuel in an existing nuclear reactor. Part 6, Future Energy. Fundamentally, All human problems come down to one basic fact: there are too many humans. Human population is growing exponentially, and unless there is a pandemic, giant asteroid or some other global catastrophe, that problem isn't going away. And even if we improve conservation, all those extra people are going to need more and more electricity. Ironically, global warming may provide part of an answer to population growth, as countries like Bangladesh sink under rising sea levels, farms turn into deserts, and hurricanes, floods and droughts become the new norm. But that's a painful and expensive way to reduce our energy needs. So, what is the future for energy in 30 to 50 years and beyond? Oil is predicted to be available for about another 50 years, and gas another 70 years, probably longer with the recent surge in fracking, and the environmental problems that brings. Coal is predicted to be available for as much as 250 years, so if we do nothing, the answer is probably mostly gas and coal. Scientists and engineers have been trying to remove CO2 from coal and gas-fired power plants for decades, but so far there has been little progress, maybe because the utility companies don't want to cover the extra costs. One interesting recent development is to use waste CO2 from power plants and industrial facilities, to feed algae, to produce biofuel. Algae are the fastest growing plants on the planet and can be processed into biodiesel. Given that coal and gas are likely to be the biggest component of electricity production for at least the next 20 years or more, you would think there would be more research and development of CO2 capturing technology. In researching this video, unfortunately, I have found very little evidence of significant investment and research into the subject. Renewables will become a big part of the answer, but will they ever answer all our energy needs? It is possible. A 2003 study concluded that the world could generate 2 million terawatt-hours per year from very large-scale solar power plants using 1% of each of the world's deserts. That's 120 times the world's current electricity consumption of 20,000 terawatt-hours per year from just 1% of each of the world's deserts, and that's using existing technology. We would need new, more efficient ways of shipping electricity around the world to take advantage of solar power on a worldwide scale, but it is a very interesting possibility. Wind power generation is becoming common in many parts of the world, such as Northern Europe, but it is not without its critics. Most people don't want giant wind farms in their neighborhood. And wind is very limited in the number of places in the world it will produce reliable, consistent power. New hydroelectric projects are usually met with huge opposition from local people affected by loss of land, and studies show dams can cause more greenhouse gas released into the atmosphere than similar-sized coal power plants. Large-scale use of fusion power, by most accounts, is still 50 years or more away, but maybe that's because there is currently only €15 billion or so invested into fusion research projects, over the next 15 years. That's what the US spends on Iraq and Afghanistan in just 1 month, or less than half what was spent to develop the atom bomb and about 1/10 of what was spent to put a man on the moon. Would spending more money make fusion happen faster? I don't know, but the Manhattan Project developed the first A-bomb in just 3 years, because it was a national priority. If fusion really is the ultimate energy source for our planet, shouldn't the world be investing a lot more into it? Thorium-based power should be far cheaper and faster to develop than fusion, because there is very little new technology involved, and small thorium-based power plants could be located closer to customers than large-scale renewable energy projects, reducing the cost and logistics of long-distance power distribution. The future of energy over the next 20 to 50 years will likely continue to be based on fossil fuels, with an increasing percentage of renewable sources, especially solar. Fission is probably too far away to be considered part of the 20 to 50 year time scale, but perhaps thorium, with a major commitment, could significantly help bridge the gap to practical fission energy.